So imagine we want to measure how far away an object is by how bright it appears. Well, we can go through and think this through. So imagine I have a light bulb. That's 100 watts. So remember, watts is a measure of energy. It tells you how much energy per second a light bulb puts out. So that tells you what we call luminosity. So as the light bulb puts its light out, it puts it out in a giant circle around the light bulb that has a surface area of 4 pi the distance squared. So that's equal to the area that the light shines out from. So if I'm going to look at this light bulb with my eye, for example, I am going to only intersect a small amount of the light from that light bulb. So you could imagine my eye has, for example, a little radius of equal to 5 millimeters. So the area of my eye is equal to pi times that radius squared, or 5 millimeters squared. The fraction of the light bulb that my eye intersects, then, is the area where all the light is spread out, so that's 4 pi d squared, compared to the fraction that my eye intercepts, which is just this small little piece of area of 5 millimeters squared times pi. So if I were, for example, 10 meters from that light bulb, then the fraction of light that my eye intersects is going to be given by the quantity of pi, 5 millimeters squared, divided by 4 pi, and then that distance is going to be 10 meters squared. And I can cross out the pi, and I can change my units of millimeters to meters, and we get a very small number of 2.5 times 10 to the minus 7. So I get a less than a millionth of the light of that light bulb. But we astronomers don't just use our eyes. We might well use a telescope. A telescope that was, if it's very small, 50 millimeters in size. And if I do that same calculation here, instead of being 5 millimeters, I'm going to have a 50 millimeters up here squared. Everything else will be more or less the same. The distance will be the same of 10 meters. And so when I do that calculation, because my telescope is 10 times larger in radius or diameter, the amount of light it collects is the square bigger than that because the area is square. I get a lot more light. So 100 times more light. So when we describe how bright an object appears, we don't want it to depend on how big our eye is. My eye, for example, is maybe a little bigger or smaller than someone else's eye. And a telescope is certainly larger than my eye. And so that comes up with how we measure brightness. The way we measure brightness is known as flux. Flux is defined as the energy received per unit area. And so no matter what I look with, the flux will be the same, and how bright the object appears is going to depend on the area of my object. So brightness and flux are more or less equivalent. So if I want to measure the flux of an object, I need to take the energy per second, which is what flux measures, energy per second divided by area. And for a light bulb, that's its luminosity. And I need to divide by the total area that it's spreading its light out to. So that's the surface area, 4 pi times the distance squared. So the flux of a light bulb is its luminosity in watts, or energy per second, divided by 4 pi the distance squared. Now, I can go through and imagine I want to know how bright a light bulb appears depending on how far away it is. If I want to know what the ratio of fluxes is between a light bulb at one distance and another, then I go through and just take this equation in the first observation, so L1 divided by 4 pi d1 squared. That whole thing divided by L2 divided by 4 pi d2 squared. And I can simplify crossing out the 4 pi's. And I get L1 over L2 times d2 over d1 squared. Now, if the light bulb, of course, has not changed in brightness, then L1 is equal to L2, and this becomes even more simpler. d2 over d1 quantity squared is equal to the ratio of the fluxes. In other words, an object's flux drops as its distance squared. So we know that as the inverse square law for light. And we can use it to then translate how bright an object appears into a distance. So imagine I have a light bulb. And I have a light bulb at one distance, and I have a light bulb at another distance, where these two distances to my detector, for example, my eye or a device that measures how bright something is or its flux. Let's say in one case that distance is 1, and in the other case the distance is 2. Then the brightness of the object, if it's in the first case, if it is measured as being 4, in the second case, where the object's twice as far away, it will measure much fainter, or 1, 4 times less, the ratio of the square of the distances. In other words, F1 in this case is equal to F2 times D2 over D1 squared. Or, in the case of my light bulb example here, I have that F2 is equal to 1, and the ratio of those distances is 2 squared, or in other words, that F1 is equal to 4 times F2. Now, when we're measuring objects in space, what we want to do is to rearrange this equation and figure out what the ratio of the distance is. So rearranging F1 over F2 is equal to D2 over D1 squared. In terms of the ratio of the distances, I find that D2 over D1 is equal to the square root of the fluxes, inverted. And so that is the way that we can imagine going out and measuring the distances, or at least the relative distances, of two objects based on how bright they appear. The next thing we need to do is to have some sort of light bulb in space whose brightness we can use. And the obvious thing to think about are stars.